is a few upcoming events. And also, so everybody knows, this is being recorded. I started it before some of you may have joined. But there is another webinar on Geothermal Rising's Full Steam Ahead series. Tomorrow there's going to be an EGS webinar with an update from Fervo. There's going to be an update from Jen Asimo, who's another one of our Pacific Northwest rig leaders, and she's with the Pacific Northwest National Lab, and she's giving a presentation on September 5th on their research. Of course, GRC, the Geothermal Rising Conference, is coming up in Reno and at the end of October. I hope everybody can make it. That is really a don't miss it event. My first one was 2 years ago, and I was really inspired by it to really get much more deeply involved in geothermal. I talked with someone from the Department of Commerce about that. There's a trade mission to Poland and Ukraine coming up in November, focused on a variety of aspects of rebuilding Ukraine. But one of the parts of the Ukraine rebuilding endeavor is the energy infrastructure that, of course, has been decimated by the war. I thought I'd let people know about it. It's California, state of California and the state of Washington are leading a delegation. It'll be a larger conference in Warsaw, but they'll have a whole bunch of people from Ukraine. And I think they'll have a smaller trip down to Lviv right at the end of this. So wanted to let people know about that. Let me know if anybody's interested in working on that. And finally, we haven't nailed down the venue or the date, but we are planning a holiday party in Seattle in December. So with that out of the way, let me pass this off to Nick. Let me stop sharing and let Nick take it away.
Sure. Thank you. So can you confirm that I'm sharing the correct screen? Is that
Looks
full
good.
screen for you?
Yes, looks
I
good.
see it.
Yep. Good. So my name is Nicholas Fry. I'm the Thermal Energy Networks market lead for Jacobs in North America, but I deal with projects kind of all over the place. I'm going to try and do some broad brush strokes on introductory material for geothermal energy networks. I'll do a very brief case study at the end before handing it back over to Delano to do his full case study for the Central Washington University. So a little bit about myself. I've focused on geothermal for many years. I actually started in the higher temperature space and have what I'd like to call progressed into the lower temperature system applications. And now I find the majority of my work is doing geo exchange systems. Certainly not what I intended when I was full throttle into EGS and things of that nature, but that's what I'm doing now. And I think it's an important piece of the conversation, right? Because heating and cooling is a tremendous amount of society's energy demands. Building, heating, and cooling is something that we live with and expect almost every day of our lives. We spend the majority of our life indoors. And this is important in so many more places where climates are changing and space conditioning is even more important for livelihoods. So I'll cover some basic information again on district energy, just so that we conceptually get some ideas down together as a group. And then I'll try and turn us towards how geothermal fits into this picture and where it fits into this picture and how we can really think of geothermal as already being everywhere, applicable for use. And what I want to challenge people on, particularly my geologists in the crowd, is let's not just get tied down so hard to our terminology that we alienate the people that actually matter, who are those that have to purchase the systems, use the systems. You can use Europe as an example where there's a lot of district heating and cooling in place. The majority of those customers have no idea where their heat comes from in the first place, right? We should kind of think of that as geothermal systems. Customers don't care if it's geo exchange or geothermal. So I'm just going to keep it basic like that. I'll end with the University of Georgia at Athens case study to tie it all together, all the concepts that we've painted, hopefully. So, you know, obligatory, what is Jacobs' giant uh, corporate empire? It is 45,000 folks doing scientific and engineering services across the globe. Inside of my group, which is energy and power, you might imagine that we work on transmission and distribution. I work on planned geothermal communities, aquifer thermal energy transfer systems, borehole thermal energy storage systems, and geo exchange. So at the end of the day, though, we're talking about design. Design practices need to change in order for us to get to the business as usual combustion-driven heating and cooling systems to what are geothermal energy networks. And that means a fundamental shift in a lot of things, including architecture and engineering. The way we think about designing our built environment, right, for lack of a better word. And Emery Levins has some great context here by skimping on the design. Basically, it comes at cost to all of us, right? We can do better. If we do better design, we're going to get geothermal in a lot more locations than we currently do. District energy has been evolving since kind of the late 1800s with the Birdsell-Hawley's Hawley Steam Combination Company. I think that was Lockport, New York. So that was steam boilers distributing the first generation district heating systems from that central plant to customers, right? And so those were operating temperatures in excess of 200 degrees Celsius. And then over the decades, fast forwarding to today, we can operate hydronic distribution networks or heating and cooling systems at scale, these district heating and cooling systems, thermal energy networks, between what is less than freezing, upwards of, typical normal range is 80 to 90 degrees Fahrenheit. So that also means that we can change that steam boiler into many different resources. So we have to think of everything around us now as a source and sink. Well, what is both a source and sink as a medium? That's the earth, right? So that can introduce more and more needs, more and more applications for subsurface systems of any applicable temperature that's accessible, whether it's near surface or deep direct use applications. So the first recorded geothermal district heating system was 1330s France. This used relatively low temperature surface manifestations, hot springs that were nearby to distribute hot water under the structures, okay, through conduits, right? They just had basically trenches going underneath the structures to heat the homes. And this system was upgraded and has been upgraded over the centuries. And it was the first regulated geothermal district heating system as well. And it still exists and is operated today. The oldest geothermal district heating system in North America is the Boise, Idaho system. I'm not sure if others are as familiar with it, but this was the inspiration for Reykjavik, Iceland, to develop their geothermal systems for district heating. And this system, if you're not familiar, just won additional water rights access for the city of Boise. And it looks like they may be interested in expanding this. So again, developed first in the 80s, already operating at relatively low temperatures compared to steam combustion systems. And now that 1880 system is going to continue expanding through this century. But we can do things without producing high temperature fluids from the subsurface as well. Basically using Earth as a storage medium. So this becomes the concept of the Earth energy battery, right? But it changes some of our completion types in the subsurface. So for those of you that are used to working on conventional geothermal systems, you're looking at something like that on the right side of the screen. This says EGS or hot dry rock completions, but of course this can be many variations. You can have this into fluid bearing reservoirs as well. Some differences is you may have some casing in unconsolidated zones for geoexchange, but it's preferable that grouted completions like the conductive borehole heat exchangers on the left side of the screen are fully grouted from the bottom of the hole to the top of the hole. So there are some open loop completions as well. And what happens is the cost to the customer basically changes, which Delano, I'm sure, is going to elaborate on later. But closed loop geothermal systems, geoexchange systems are quite expensive as an option. And for completions in unconsolidated zones, then you may limit the total drilling depth, which is a fundamental challenge in urban environments or places with high demand densities. So you might think of that as campus energy systems, healthcare, downtown districts, those sorts of things. Considerations then turn more to the lithology that you're going to encounter and how you're actually going to complete your bore field or your well field in place in order to match the loads completely. Balancing these systems becomes pretty important if you don't have advective flow in formation to essentially wash away your thermal plume and renew it, because you can thermally saturate the systems where you either increase or deplete your temperatures in the reservoir and reduce the system's overall lifetime. It's typically less important in open loop completions. There are some novel variants that try to avoid producing fluid from the aquifer entirely. These are expensive. They're good solutions for specific places where regulation is ornery, is what I would say. There's aquifer thermal energy storage, which is a good, nice low temperature application. These systems were first developed in the United States, and I want to say it was the early 1960s. Then they proliferated quite a bit in Shanghai, so everything kind of went over to China. They've gotten good adoption rates in the Netherlands and Northern Europe in particular. Sweden has a lot of aquifer thermal energy storage systems as well. And so you're just using the seasonal demand differences from the building to store a thermal plume in the subsurface at different locations or elevations in an aquifer system to improve the performance, typically of heat pumps at the surface. So the heat pump is a vapor compression cycle. For every 1 unit of electricity that you put into that, you get X number of thermal units of energy out of that system. So if you're getting a coefficient of performance of 4, that fundamentally means that you're putting in 1 unit of electricity into the vapor compression cycle and you're getting 4 units of thermal energy out of the system. Do the math, that means you're getting 3 units of heat out of the ground, 1 unit of heat from your vapor compression cycle, adding up to 4 units of heat in the building. Or in this case, your thermal energy network. So there's a very, very limited workforce in North America for drilling, professional drilling for geo-exchange in particular. It's mostly based out of the water well drilling business, which is oftentimes very different than the oil and gas workforce, different standards, different organizations, different associations. You'll find that there are cases where oil and gas workforce and historically oil and gas drillers have made their conversions over to geo-exchange or geothermal drilling in this small space. But relatively speaking, you might be thinking of only a few hundred people inside of the United States that are working on a regular basis for geothermal or geo-exchange drilling. Leaves us with a pretty large deficit, and you can see that by increasing linear feet of drilling costs in the United States over the past 5 years or so. So what if our capacity of our bore field needs to be reduced because the client doesn't have enough money? This is a very simple problem of hybridization. There's so many different ways you can hybridize the systems. Oftentimes you'll find that commercial structures all the way up into the Yukon are cooling dominant. And you can thank the architects for designing those structures as being cooling dominant. And that means that you're rejecting more heat to the ground than you need to extract from it. So you need to manage your thermal battery in the subsurface, right? There's several ways you can do that. You can do that with open bodies of water or dry coolers or some auxiliary waste heat source. The alternative is, of course, if you have heating dominant loads and you need to condition your borehole array back up to a minimum fluid temperature or temperature inside of the rock volume, then you need a supplementary heat source, right? And the same can be true that dry cooler can reject to ground as well. You can think of operationalizing that in the shoulder seasons, so you're preparing for winter. Winter is coming, right? So when you have that network in the ground, one of the benefits is also to reduce the size of your bore field or your geo exchange system, is that you can, instead of hybridizing through auxiliary equipment like dry coolers or supplemental heat sources, you can count on what is heat recovery across the network itself. So buildings are demanding heating and cooling at different points in time. And sometimes this can be instantaneous. And this, simultaneous load can then be shared across that network and therefore basically cancel out the need for producing additional primary energy to meet those demands. Okay. That has a number of benefits, but one of the primary benefits being capital cost reductions. That means it makes geothermal systems more accessible to more people. And if we go to the gas systems concept, right? So we have a utility network operator now that has to sell some product to customers. This means that not everybody has to drill their own geothermal boreholes. We can network everybody's neighborhood, and this geothermal energy network can replace our existing gas systems. But then that's an electrification approach, right? So all of this is electrification where we have distributed heat pumps and distributed borehole arrays. So the utility model side of this works, but everything about this then becomes highly dynamic. So those are the design challenges and some of the insights into the solutions that designers look at with some regularity. Uh, then we scale this further. There's still the built environment which we have, not the one that we wish we had, right? So what I'm saying by that is a lot of buildings are built for sometimes 180 degrees Fahrenheit and above. We've got buildings in downtown New York built around the steam systems, right? So if you want to, for example, take some of the nation's most iconic structures off that steam system, you would you would be fundamentally altering the way those buildings operate, and it may not be economically feasible. So a strategic approach in primary energy use needs to be thought about across the entire um, landscape of your campus or your city in those cases. And you can think of the geothermal energy networks being applicable at almost every one of these locations, whether it's deep direct use or geo exchange. You can meet these operating temperatures, but then going back to that concept of load sharing, you strategically move energy through the fluid conduits in your streets instead of the gas conduits to where it needs to go to reduce primary energy consumption at scale. All right, so now we're on to, we have all these concepts down about geothermal energy networks. We'll just move on to a very brief case study at the University of Georgia at Athens, where we kind of tie it all together. This is legacy systems in operation, had 6 to 7 distributed energy plants or districts already operating at different temperature regimes, kind of like you would see in a city landscape where you might be thinking about the same applications, right? So how do you handle this in reality? We've got steam, we've got distributed hot water, we've got chilled water systems, and how do we tie this all together in a reasonable approach? Well, if we go back to that concept of moving energy to where we need it to go, um, and introducing the concept of energy arbitrage, which is the time of use and choosing that time of use for the energy that we produce from the system, that Earth battery, the geo exchange system, can become what is a fundamental component of decarbonization for campus systems. So you have to kind of go through the iteration of where am I going to put these thermal batteries? What are my heat sources and sinks? What are the applicable funding mechanisms? And how can I operate as efficiently as possible, right? So instead of just designing to lowest capital cost, we can design better through performance-driven design initiatives. And in retrofit, that can be challenging, but for the University of Georgia at Athens, we were able to find a solution with the ability to put in about 3,000 boreholes, geo-exchange on the south side of campus, underneath some existing intramural fields, and then take advantage of an existing railroad corridor to install our geothermal energy network. This geothermal energy network is there to actually improve the performance of the distributed plants. So there's now, you can imagine, 4 distributed energy plants at various locations, all able to share energy with one another. So instead of each structure having to share with one another, you can imagine hundreds of buildings versus 4 distributed energy plants. We can allow those districts to gradually decrease their operating temperatures and become more efficient over time while taking advantage of both geo exchange and load sharing between those districts. So this is kind of the holistic thinking about how you get geothermal energy networks everywhere. The convenient fact of designing better is also that it's the lowest cost pathway. So we can beat high energy use intensity of legacy structures with geothermal energy networks. Um, and this is an example of one of those cases. It's, optimal resource utilization or resource efficiency in this case. So last thing I'll mention are the training tracks. If there's any aspiring drillers out there, I would encourage you to go for it. There's a lot of great resources from National Groundwater Association and the International Ground Source Heat Pump Association. We've, of course, got great information to share at Geothermal Rising as well. One of the first places that you can get started on the basics are, becoming what they used to call an accredited installer for geo-exchange systems. Now they call it a ground heat exchanger installer. Those courses are available on the IGSHPA website. There's two books I would encourage you to peruse if you ever get over to your library. The second one might be a little harder to find in the States, but that's a Canadian author. These will give you an introduction to the how-tos and keeping track of maybe you're an engineer, a geoscientist, tracking contractors out there. This will give you some basis on what you should be managing too, and how those installations actually work, which is fundamentally very important for system operation. All right, so there's some references. I'll turn these slides over and I'm going to pass it on to Delano for the case study.
Yeah, well, thank you, Nick. That was fascinating, and I really appreciate your hitting the workforce development implications of that. That's a real need that we are going to have. So, thank you so much. So, if you can stop sharing and then let Delano tee up his deck.
While I'm bringing this up, Nicholas, I do have a question regarding that workforce placement. Is there a degree that's required prior to going for that certification for the drillers?
No, there is not. And there's various forms. A lot of states, it depends on jurisdiction, but a lot of states adopt what are the AGWA guidelines, the National Groundwater Association guidelines, which are published. And that's kind of a basis. But the drillers, often what I prefer to do is if you're looking for geo exchange drillers, they should have what is a certified vertical closed loop drillers certification from NGWA. That's a nice certificate to have, but no degree is required for that.
Okay, all right. I'll try to keep this at 20 minutes as much as possible so we have time for the Q&A at the end. So thank you, Nicholas, for the lead in, and it's a great and pertinent information. So he was obviously giving you the University of Georgia. I'm going to give you the Central Washington University. First of all, are you guys seeing my presentation full screen, or are you seeing the presenter mode?
Full screen. Good.
Full screen. Okay, fantastic. My name is Delano Palmer. I'm the Director of Capital Planning and Projects here at Central Washington University. Been here since 2018, and then before that, 11 and a half years in a private sector for design build firms doing projects across country. So I've really enjoyed my time at Central, being able to transition an entire campus for college students is pretty awesome because you get to see how it impacts their lives. And I have fond memories of my college days, so it's pretty cool to watch a whole campus change. So first and foremost, I gotta thank the engineers that we have been working with throughout our process of doing geothermal. A lot of the content of this presentation is being provided by them, so I want to make sure that they get the read or the recognition. Geoengineers is the hydrolysis that we've been using on GeoEco 1. We also have been using Aspect Engineering, who is the hydrolysis on GeoEco number 2. MW Engineers has been focused on the engineering associated with our existing geothermal wells, and then McKinstry has been helping us out with our decarbonization and campus conversion efforts for the future. So, and then all of this obviously was helpfully funded by Washington's Climate Commitment Act. So I want to make sure that was in there. All right, so I'll try to go through this as quickly as possible because I got to kind of go high level and then down to some of the details. So this really starts from a legislative standpoint on what the push was to be able to do this. There were two primary things that we have been going to comply with. House Bill 1257 is a clean building performance standard, but 1390, the decarbonization, is really the thing that's been pushing us. And if you're in Washington State, you know that this is a 15-year plan to decarbonize. Now, that plan is skewed from 15 years because of, unfortunately, the state has been in some deficit. So funding that institutions were hoping to get to start implementing those plans is being slowed down. So we're thinking this might be a 17, 19, 21, possibly 23-year plan based upon our funding distribution. But this is the impetus of why we are doing this thing as a university. We also developed our own climate action plan that was left by Jeff Busan, who's our sustainability officer here at the university, to be able to realign our vision and values that chase a really healthy and sustainable future. At the end of the day, these are the metrics that the state is judging us on. The whole initiatives associated with 1390 is reducing the carbon emissions of our campus. We currently have 4 natural gas-fired boilers that provide steam to the majority of campus. We have some standalone systems throughout, but the majority is off of natural gas steam. Their desire, our aspiration is to be able to convert that and move move heavily on geothermal. We do not want to remove our natural gas systems nor the steam vaults. We're going to be keeping using those because we feel as though resiliency and redundancy means that you have 2 means of heating and cooling. And so we'll be maintaining that. At the end of the day, we're trying to lower our EUI and cut down 88% of our annual reduction in emissions. So that's why we're doing this. We started very similar to what Nicholas was talking about is with the University of Georgia, is looking at the different types of district energy systems that we could implement. So we started with, steam, we started with hot water, we talked about high temperature, we talked about combustion, the things that we were looking at. We would love to be able to do some things that are non-combustion in the future, but for the time being, we had to work with what makes the most sense for us. And as we started going through this, what really led to the best option for our campus is an open loop, a geothermal nodal system. And we'll dive into that a little bit more on what that looks like. We also have the collection of existing dual stage heating sources around campus, and you'll see why as we get into the actual district heating system that we have on campus as we convert to our future. So as I mentioned, the diagram here is showing our high level of what the current layout of campus is. We've got the 4 natural gas fired boiler providing steam throughout. That's going to be essentially a backup. And the number 1 is indicating the geothermal wells for GeoEco number 1, or that's the GEP plant, the mechanical housing plant that we use to be able to actually do the heat exchange. Essentially, we will have 2 heat recovery chillers in that GEP plant, and they will be serving low temperature hot water and chilled water throughout campus. The intention is that we're going to take advantage of our chilled water loop to continue pushing that water around for our cooling service. And then we would expand our low temperature hot water loop that's currently serving 3 buildings. And eventually we'd expand that to serve all the buildings on campus. Again, not replacing our steam vaults, but simply supplementing it as an additional service, a resilient service. This shows you exactly what we have there as far as existing heating, as far as our hot water supply. So I just wanted to kind of show you the makeup of our campus, where we're having the most demand and highest temperature usage throughout our campus. This is another way of talking about the conversion strategies that we're essentially looking at. So some of the buildings that we're already using, the light blue, the teal, is the ones that are on low temperature hot water loop. So the one towards the north is where the North Academic Complex is being installed, and the 3 to the south are where our science neighborhood are. And as you can see, most of this, what we've been doing is boosting our hot water temperature. And so this is an opportunity to make the conversion that it would be on an exchange system with our low temperature hot water. And that's really the primary or heaviest expense of our conversion, along with the GeoEco plant will be extending our low temperature hot water loop. As we started planning this on a master plan level, what does it take to be able to convert our campus? We've been working with our local municipalities to ensure they're prepared for the electrical load associated with our geo plant. As you can see from a base level, we do have a peak demand right now, about 10 megawatts. The campus itself operates on a base level of between 4 to 6 megawatts. As you can see, the city is able to cover us and support us through 2026 when they plan to jump up to 20 megawatts because the university and a large food distribution warehouse is coming to the city. And so they're ensuring that they've got more power from BPA coming up, which will account for our GeoEco 1 and our GeoEco 2. And then you can see they're going to have to make another jump over in about 2036. So we've been working with them on a long-term strategy to make sure they support us. But if you can look at just at CWU's line and the demand that we're going to need, we're almost 4xing our electrical demand by the time we do this full conversion with this open loop geothermal. This is kind of showing you the map orientation of how we're going to phase this in. So we've got different phases on how we're going to implement and connect it to the different portions of the campus. And then this is given a roadmap on the cost of this. And so this is part of our decarbonization plan that we had to submit to the state and show them the overall cost of this project. And when it comes down to it, our cost was between 350 million to almost 400 million. That's on a 15-year plan. Now, again, because of the state budget, we know that's not going to be the same case. So those numbers are going to jump. If you were to add up all higher education, I would say that you're probably in a neighborhood of maybe 8 to 10 billion. UW has a massive amount, so does Wazoo, and everybody's going to be going to some sort of heat pump system. It's whether it's air, water, or ground. So we'll jump into the actual design of the geothermal system that we have for our upcoming building. So it's supporting this new facility that we're building, the North Academic Complex, which is known as the NAC. For those of you that got to join us in April, you got to walk this facility as it's construction. It's scheduled to be open next year, but it's 106,000 square feet. Has 19 classrooms, a whole bunch of offices. It's a 4-story atrium that'll have solar array on there. And once what's completed, it'll offset 22,000 metric tons of greenhouse gases over its 50-year life cycle planning. This gives you the outline of the campus map to kind of show you where we're at. So during our April study, we were in the building below, which is Discovery Hall, but this is also showing you where the North Academic Complex is, the supporting GeoEco plant, and the injection and extraction wells. The injection well, we actually just moved a little bit further to the southwest to ensure that we ensure that when we plan future wells, to what Nicholas was talking about, we have to be cognizant of the energy plume that we put back down into the earth on an open loop so we don't disturb it or cause an issue for recollection on a future extraction well. Inside the GeoEco plant, we're using a 6-pipe heat pump system. So you can see the green piping there is reflecting groundwater that is coming from our well before it goes to the heat exchanger system. Red piping is representing our district low temperature hot water and return and supply. And the same thing with the blue pipe, and that's representing our chilled water supply and return throughout campus. And this is just an example of what that will look like when it's installed in that facility. And then also the heat exchanger. This next video is a model of what that GEP plant will look like. And what CW is doing is going to be using this as an opportunity to collaborate with our faculty as a learning opportunity. So as you see there, it will be open glass on 2 sides so that people can walk up and learn how the GeoEco plant works. The 2 boxes right there beside us, are the 2 heat recovery chillers. You have all of your supply pumps. The extraction pump for this will be mounted in the well. It'll be 250 horsepower. We're going to be going for 2,500 gallons per minute, which we tested successfully on the extraction. We're almost done with the injection well, and we're going to be testing pump testing that as well. Now, as part of this collaboration on making this an active learning center that people can go up to the outside of the facility and learn it, we are introducing color jacketing on our piping. This is so that people that from 4 years old to 99 can learn quickly how geothermal works, the heat exchange process, and be able to trace the piping here. And so we think this is going to be a really high selling point for people that may be interested in this field, or even if you're not interested, making sure that you have a general knowledge of how this works. So we're really excited about the concept of this facility that MW Engineers has really helped us out, and McKinstry has helped us plan out for the future. And even this plant itself will have a solar array and give a really great representation of what Central Washington is about. Now we're going to jump into what our campus is made of. So first, we'll look at our campus in a 3D model. Again, this is generated by MW, and it's going to show you where our North Academic Complex, and what these maps are intended to show you is our heating water network first. So it'll come up really quickly. And that kind of shows you what the low temperature hot water is doing, serving a couple of our existing facilities, along with the North Academic Complex to the top of the page, and the future GEP1, which is kind of the black box at the very top. Our existing central energy plant is the small box all the way to the left of your screen. The cooling water network is the chilled water system that serves the majority of campus. Again, we'll be taking advantage of this to push our new chilled water from both the GEP and our central plant across campus. We have 4 1,200-ton chillers in our central energy plant. So cooling capacity is not really an issue with our university. And this will show you a combination of what the campus heating and cooling water network looks like together. Now, for the basis of being able to exchange heating between 2 buildings, as you can see here, the GeoEco plant will allow us to be able to exchange heat between other buildings on campus that are served by our low temperature hot water. So as we go through this model, you'll see an exchange where one building is calling for heating and one building is calling for cooling. You'll have the exchange, and then very quickly, you could actually modulate this where there's not a high demand on both facilities, but they can actually heat appropriately. So you see the lower colored associated with those facilities. So we're really happy about this. Once we get to expand this across campus, we won't have the issues that we have with shoulder seasons where we've turned off heating and it still gets a couple of cold mornings in the buildings, and it takes a lot to heat up, and vice versa in the fall when we haven't quite turned on the heat yet, but it's still pretty, or we've turned on the heat and it's still pretty hot. Those last minute hot November days throw us off balance. So it's going to be an amazing system when it's done. This is an image of the GEP plant that's in progress across from the North Academic Complex. We're on foundation walls, so this was just taken a couple of weeks ago, about 2 months ago. And now we get into the actual well construction itself. So the well construction is relatively close to the North Academic Complex, really across the street. On the right side of this picture is that GEP plant. We've already completed the extraction well at this location. This gives you an idea of being able to figure out where we dug. There are 2 aquifers in our region, so we dug down into the upper formation for the extraction of the well water that we're using on this. We dug down to 1,100 feet. We found optimum conditions at around 500 to 800 feet. And for the well size of this, we have a 20-inch well, and you can see how we broke up the screen distribution on that well profile between 500 and 800 feet, beg your pardon. And this is just a couple more interesting photos associated with how they dug this well. So chemical disbursement, surge in their pumping, and then they transported and disposed the well extraction material over in a area that we designated on campus. This gives you some more profile information associated with this plumbness. They did do that 53-hour pump test on that extraction well, which was successful at holding its performance. So the primary goal here is to get to, 2,000 gallons per minute, not 2,500 gallons per minute. 2,000 gallons per minute was our target, and we achieved that. So we're pretty happy with that information that we got. So this is more technical detail that was done by our hydrologists, geoengineers, to ensure that the recharge capacity on the well can handle the demand that we were talking about. So that was a real big issue and question about this, and it will play a huge issue as far as the placement of our future extraction and injection wells. So this is giving you information associated with the projected drawdown associated with those wells. And quite frankly, these are all information that me and my team have been really just amazed at learning. This has helped us to kind of develop our skills a little bit more, but we're still very novice in all this information and learning as we go. So geoengineers and everybody we've been working with has been great with really breaking this down into elementary knowledge so that we could make sure that we could pass this along. And we've been sharing this with our student body and faculty so that they have an opportunity to understand a little bit better. And so we've got great videos of the weld inspections, sediment accumulation, and then we did modeling associated with what does that thermal plume look like from an extraction and injection point, and how far the injection well needs to be from the extraction well. So we're doing the injection well now. We're feeling pretty confident about it, especially because the area that they dug into was really some basalt. And so we have some pretty heavy rock there. So it's great for water dispersion. We have a 250 horsepower extraction well pump that's pushing it, that we're hoping to gravity fall, but we are planning on having a supplemental pump if necessary based upon the back pressure. So once we do the testing on the injection well, we'll understand whether or not we're going to need that supplementary pump for injection. So with that, that is all my information. Oh, one last thing I should share on my screen. In case you're interested in following us, and I'll bring this back up here on our slide, is there's a QR code. I'll leave that up there for a couple more seconds. In case you're interested in getting to our live camera feed, you can see how the progress is going, specifically on a GeoEco plant. The North Academic Complex is now not fully constructed, but at least all the walls are up and everything. We've got it dried in, and now we're just finishing off exterior and interior details. So if you're interested in that, scan that QR code and continue to follow that. With that, I'll stop so that we can talk about any questions that folks may have.